Here we are yet again with another concept map for this week. And the title of our chapter is Four Fundamental Concepts. I'm going to imagine that I don't have to tell you anything further about concept maps or how mine have been constructed. We've been doing this long enough, but of course, if you still have questions, be sure you can take a little bit of time to reach out to me and we can have a conversation and talk about concept mapping. But for now, let's turn our attention to our concept map. And as you can see at the center of our concept map, there are four key concepts that are highlighted. These four concepts are not only the four key concepts for this chapter, as suggested by the chapter title, they are absolutely crucial to our understanding of inferential statistics, which is the next half of the text. Let's focus first on random sampling, and we'll go down and to the left in our concept map for this purpose. You'll note that random sampling involves selecting cases from a population, and you might be quite familiar with some examples at this point. For example, think about a most recent election, and let's say we're interested in what percentage of the population will vote for a particular candidate. Clearly, surveying an entire population is bound to be impossible, if not impractical, so we need some other way of determining, at least as best as possible, what percentage of the population will vote for a particular candidate. So we need to choose people from a subset of the population, but this subset needs to be representative of the population itself. All the same, and there are different techniques, we need to ensure that we select people from the population in a particular fashion. The first requirement entails being able to choose anybody from the population with the same chance of being selected. So let's say you had a list of everyone with a cell phone in a particular city, and you use that as a basis for identifying particular possibilities for a random sample. Of course, this is going to create some problems for you because not everybody has a cell phone. So what do? In any event, not everybody in the population has an equal chance of being selected because not everybody has a cell phone. Furthermore, a person should not be selected from a population based on other individuals in the population. So for example, let's say you're conducting your survey and walking down a neighborhood and randomly chose a particular house to stop by and said to yourself afterwards, maybe I'll just stop by the house right next to it. Well, that would not be choosing that individual to participate in your survey in an entirely random kind of way. Last but not least, we have to recognize that any sample is entirely possible, although some might be rarer than others. So for example, let's say you were out doing a survey, there are 3 candidates running in the next election, and your entire sample just happened to identify a particular character in the election for their choice. This would be rare, but more importantly, the sample most likely would not be representative of the population. So how do we ensure that every participant that we choose for our sample is chosen with the same equal chance of being selected and done independently? Well, Caldwell doesn't take this up in a particularly detailed fashion, but for our purposes here, I'll point to 3 different kinds of techniques. Please simply take note of them. The first one is called the simple random technique. A second one, referred to as the systematic random technique, and the third one, stratified random technique. Each of these 3 techniques does not adhere in the same way to the basic principles of random sampling. Some are better than others. But from time to time, there are practical matters to consider, and so as a result, our random sampling technique needs to be modified. In any event, doing a random sampling technique requires knowing your population of interest. In other words, the particular characteristics that are relevant to your research question, for example, as they pertain to the population that you're interested in. Knowing what your own population is allows you to create a list of all possible members from which you would select from in order to construct your sample. A full list of all possible members in the population is referred to as a sampling frame. It's important to remember, though, that not all sampling frames are complete. For example, you might be conducting a survey based on a sampling frame that uses people's telephone numbers, in particular, cell phones. But as we all know, not everybody has a cell phone, and not everybody lives in a home with a particular address. So that might be problematic as well. If you think about the homeless, if you think about elderly people living in senior citizens complexes or other similar places, they might not appear on your list. And as such, those individuals do not have the same chance of being selected to participate in your survey as someone else who might live in their own home or have a cell phone. This brings us to the second big idea for this particular chapter, namely sampling error. When one is going out and conducting a sample, identifying a sample for, say, a survey, one has to remember that in calculating a particular sample statistic, that it might be different, it's likely to be different, in fact, from the corresponding population parameter. This is due strictly to chance, the chance of being selected to be a participant in a sample. Remember that one could construct a sample of any given size and any different composition. So we would have a large number of possibilities for our samples. And as such, not every sample is going to be a good representation of the population that we were interested in. And as such, we're bound to see some errors between a sample statistic and the population parameter. So for instance, if you were to calculate the mean age for a particular sample in your city and compare that to the population age, there's bound to be some difference. One might be higher or lower than the others. It's also, of course, possible that they could be equal. The third concept of our four concepts for this particular concept map is called the sampling distribution. It is, in essence, a distribution of samples. Imagined as a visual, we're looking at a distribution of the sampling errors. That is, the differences between the sample statistic and the population parameter for any and every particular sample in a distribution. For the most part, we'll just be looking at sample means, but of course we can look at sample distributions that can be constructed for sample medians, sample deviations, and sample ranges. The sampling distribution for a sample mean is going to have particular characteristics, and it's constructed in a particular fashion. Sample means take many different samples from the same population. In the end, when we look at the sample distribution itself, it is going to have a mean which is equal to the population's mean from which they come from. And last, like all distributions, it has to have a standard deviation as well. In this case, we know that the standard deviation is equal to the standard deviation of the population, except we're going to divide by the square root of n, small n, which represents the number of elements in the sample. This particular standard deviation has a special name, and it's referred to as the standard error of the mean. Last but not least, this brings us to the central limit theorem. A theorem is a mathematical idea, an important mathematical idea. A theorem, mathematically speaking, is referred to as a formal statement that can be shown to be true by logic. I'm not going to pursue it much further here, but I will reiterate the main points from the text at this point. And there are 3 points here to keep in mind. Central limit theorem says, for repeated random samples of size n, which are taken from a population which has a particular mean, a mean identified as mu, and standard deviation which is equal to sigma, we know that the sampling distribution of sample means will have a mean equal to mu as well, and the standard deviation is equal to sigma divided by the square root of n. The second key point that is important to raise at this moment is that when we increase the sample sizes, in other words, as n increases, the sampling distribution itself will begin to look approximately normal. And last but not least, the central limit theorem also says that the more samples that we take, the closer the sampling distribution will be approximately normal as well. Here ends my review and reading of 4 fundamental concepts through my own mapping. I wouldn't be surprised if you came to me and said that some of these ideas were a little more abstract. So let me advise you this way. Take a darkroom moment, as Caldwell would say. Put your book away, go for a walk, come back, take another look at your book, read some more of the examples. And I suggest that in time, these ideas will become a little more familiar. If, on the other hand, you are ready, you might turn to the questions at the back of your chapter or continue along with your work with your peers. Until then, this completes this week's concept map.